In this video I want to show you two examples, right? Two examples that are taken from our homework set that a lot of students ask questions about, and so I figured I'd work them out right here in a video. This is the first example, and then on the second page here you can see I've got another example for you. But let's take a look at this first example. This is an example where they give us some information from a binomial probability distribution, and we have an n, that is the number of independent trials that will be conducted, is 11, and they told us that the probability of success is 0.6, and they want us to find exactly what's the probability that x is equal to 9, right? So that's what this right here represents. They're really asking us to find the probability that x is equal to 9 exactly. Well, for part A, they want us to use the binomial probability table, which is probably found in the back of your book, to find this value. Part B has a little bit more to it, and we're going to come to that in just a second, but we're going to need possibly this idea of continuity correction to use a normal distribution to approximate the binomial. Well, we'll get to that in a little bit. But let's first figure out how this part A works here with n is equal to 11, and my probability of success is 0.6. Now what they didn't tell you, but you can probably assume, is that if the probability of success is 0.6, I think you can easily assume that the probability of failure is 0.4, right? Because these two values are complements of each other. Okay, so I'm going to use the table that's in the back of my book. Let's see if I can show you that table here real quick. And I have an n, remember that? I've got an n of equal to 11 there. So I'm going to use this table in the back of my book, and I know you can't read these numbers very well, but I'll just point them out to you. Here is my, this is page 750 in my book. This is where n is equal to 9, n is equal to 10, n is equal to 11, and I'm looking up an x value of exactly 9. So there's 0, 1, 2, 3. I'm going to scoot all the way down here to 9. Now I'm going to keep my finger in this spot right here, and I'm going to go back to the sheet. Do you see that my probability of success, little p, was 0.6? Right? My little p was 0.6. So over here in this table, I'm going underneath the column up at the top here that says 0.6, right? Going underneath this column here. So I'm going to follow this column down all the way till I get to an x value of 9 for when n was 11. And I know you can't read that number, but it says 0.089, right? 0.089. Okay, so that's using a table to determine the binomial probability for when x is equal to 9. We get 0.089 exactly. Okay? That wasn't too bad, just looking it up on the table. Now the second part as I pointed out in a previous video, this is part 2 of a total of 2 videos. The second part here says, all right, if this product of n times p is greater than or equal to 5, and if this product n times q, that's the number of trials times the probability of failure, is also greater than or equal to 5, then I can use this normal distribution to approximate the binomial. I can do that. So let's check these two things first, and if they both check out, then I'll proceed. But you're going to see something that kind of goes awry here. It doesn't quite work for us. Now remember, my n was 11. I don't know if you can see that up here. My n was 11. Probability of success was 0.6. Okay, keep those in mind. Probability of failure is 0.4. So I'm going to check these two products here. I'm going to check to see if NP is greater than or equal to 5, and I'm also going to check to see if NQ is greater than or equal to 5. Alright, our N was 11. So I'll plug that in right here. And my P, probability of success, was 0.6. And if you do that math, you'll see that you come up with 6.6. And sure enough, that is greater than or equal to 5. So that checks out, no problem. But take a look at this one over here. My n being 11, and my probability of failure is 0.4. And again, these two things here are complements of each other. So if this one is 0.6, automatically that one's 0.4. You'll see that this product works out to be 4.4. hey, wait a second here, that doesn't quite match, right? That's not greater than or equal to 5. That doesn't work out. So because, right, let me put a slash to that because that's not true. So because both of these are not true, right, I got a check mark for this one, but I got an X mark for that one. Because both of these are not true, I cannot use the normal distribution to approximate the binomial. So I'm going to stop right there and call it quits on this problem. I can't do that one. Right? So for part B, if you're using maybe something like My Math Lab, I think it says to enter in the letter N if it doesn't work. Okay, here's my second example and my last one for this video. What if I have an N of 13, right? That's the number of independent trials. Probability of success is 0.4, and they want us to find at least 6. At least 6. Probability that X, right, this is what it really means, probability that X is greater than or equal to 6, because at least 6 includes, right, this phrasing here includes the number 6, and they want me to look this up using the table. Okay, I've shown in a previous video what at least 6 means. It technically means, I hope you understand, it means probability of 6 plus probability of 7 plus the probability of 8, all the way up until I get to the probability of 13. And I'm going to sum all of those numbers together. Now that's a lot of summing to do, but I guess we can do that and we can work that thing out if we had to. Let me just point something out to you real quickly here for part A. Right? Let me point something out to you real quick. As I just showed to you, at least 6 means this. Okay? It means to add up all of these probabilities all the way up to my n, which in this case is 13. So I could sum all this and I could get my answer. Okay? This is what I'm after for part A. I could add up all those probabilities using the table and I'd get my answer. I hope you also see that I could do the problem this way. I could come up with the answer this way. I could find the probability of 0 plus the probability of 1 plus the probability of 2, etc., all the way up until the probability of 5. Now why am I stopping at 5? Because the next probability would be 6, right? I could actually find this sum right here, but that's not my answer. That's the complement of my answer. Okay, so I could actually find this sum, and once I find that sum, if I take it away from the number 1, I'll be left with my answer. All right? So I'm only showing you this because some of my students like to use Microsoft Excel to work these problems out, and so to do that you can use binom dist with Excel, plugging in your probability or your number of successes being 5, and the last number in that formula would be a 1, basically saying, yeah, I want you to accumulate all of these here, find the sum of all these, and then if you take that sum away from 1, complement, you'll come up with the exact same answer. Okay, I'm not going to bother doing that. You can do that simply with your table. The interesting part of this example, though, is part B. It says to use, if possible, a normal distribution to approximate the binomial for at least 6. Okay, now, two things going on here before I dive into this problem for part B. Two things going on. Number one is I have to check and verify that I can use the normal distribution. And do you remember, like I did in the first example, I have to check and make sure that both of these products here, n times p and n times q, are greater than or equal to 5. Well, I can do that with this problem. I can see that my n is 13. My probability of success was 0.4, if you recall. And sure enough, 13 times 0.4 comes out to be 5.2. Right? And sure enough, that is greater than or equal to 5. So there's a check on that one. That one definitely works. Let's go check out the other caveat that I've got to make sure that is greater than or equal to 5. And I'll do that real quickly here. My n was 13. These are complements of each other. So this must be 0.6. And yeah, 13 times 0.6 also is greater than 0.5. Right? That comes out to be 7.8. Should have done it this way over here, I guess, right? That's what I meant to do. Anyways, my point is, look, both of these numbers are greater than or equal to 5. Okay, so that's the first thing I had to check. In the first example I showed you, I couldn't because both of them did not give me values greater than or equal to 5. Now that I've proven that, what I'm going to do then is this. I'm looking for the probability of at least 6. And as I showed you just a moment ago, that's the same thing as saying the probability that x is greater than or equal to 6. I have shown you in a previous video what this means as far as continuity correction means. Right, so go check that out on a previous video that I have here on the Poyser Math YouTube channel. But that simply means, continuity correction simply means, oh, if you want to include 6, then you have to back up just a little bit to the left-hand side of 6 because this is a shade to the right. And so I'm going to back up just a shy little bit of 6. You know, here's the picture here. Right? If 6 is sitting right here, I'm just picking a number on 6, and I'm going to shade to the right of that, and I want to include 6, then I hope you see that I'm dealing with the number of 5.5 and beyond, okay? So I'm going to shade all this over here. That's what I'm looking for. Now the last thing is, and I don't need to prove this to you, but I guess I can just mention it briefly, and again this is covered in a previous video as well, is I can't look this 5.5 up anywhere on my table. So what I'll have to do is I'll have to convert this x value into a z value. Okay, I need to convert that into a z value. The way to do that is with this simple formula that says, hey, subtract from the x, subtract from the x the mean and divide by the standard deviation. Okay, so you're going to plug in 5.5 for your x value. You're going to subtract from that the mean. Now what's the formula for mean? It's NP. And you're going to divide that by the standard deviation. Now what's the formula for standard deviation for binomial distributions? Oh, that is the square root of NPQ. Okay. Also, this is covered on a previous video as well. So you're going to convert that 5.5 into a z value. And whatever that z value is, remember that, or I'll just write it as z-score right there. Remember that you are shading to the right. So don't look up this number directly on the table and call it quits. You want the complement of that number because at least the table that we use here for this Triola book shades to the left. So you want the complement of that. Again, covered in a separate video. I hope that helps.